Hello everyone. Today I gonna introduce this paper, Exploration of Power Savings on Multi-Core Architectures with Offload Real-Time Operation System. And my name is Chen Xingyi, and below is the paper link. Here is the outline. We will start from the introduction and related work, and we will jump to the heuristic task mapping strategy, power saving techniques, and the conclusion and future work. Introduction. A real-time operating system are essential for managing task execution in time-sensitive applications such as automotive systems, robotics, and avionics. These systems demand strict adherence to deadlines, where even minor delay can lead to system malfunctions. Traditional RTOS architectures, often implemented in software, face challenges in meeting these requirements due to computational overhead, jitter, and resource constraint, particularly in multi-core architectures. The integration of RTOS into multi-core systems introduces new complexities, like the task scheduling overhead. As the number of tasks and core increases, scheduling overhead significantly impacts system performance. And power management trade-off. While power-saving techniques like dynamic voltage and frequency scaling (DBFS) can reduce energy consumption, they often introduce latency or missed deadlines, which compromise real-time performance. The last is balancing real-time performance and energy efficiency. Achieving this balance remains a critical challenge, particularly in embedded systems where both reliability and power efficiency are essential. And a key contribution of this work paper include like offload RTOS components, like we will talk about later. Yes, in this paper focuses on the exploring of the integration of power-saving techniques in real-time systems like RTOS, equipped with offloading method without compromising system real-time performance. It means that it will not just reduce the real-time system you needed, the time you needed. The study introduced a heterogeneous multi-core system architectures comprising a network on chip (NOC) and 4 process elements (PE) arranged in a 2D mesh topology with a master-slave configuration. And we're gonna talk about 5 things. The first is the offloading RTOS components. The second is power-aware multi-core architectures. The third is energy-efficient slab PE design, and heuristic task mapping strategy, and balancing real-time performance and energy efficiency. Related work. We first talk about RTOS offloading techniques. Traditional RTOS are primarily software-based, which result in increased computational overhead, scheduling delays, and instability in multi-core systems. Existing studies have shown that offloading RTOS functionalities such as task scheduling to hardware or coprocessors can significantly improve performance, like the hardware-based scheduling. We are hardware scheduling in this paper, and usually they are using the software scheduling like we talked about before. Offloading scheduling to hardware efficiently reduce the overhead of context switch and lead to significant performance improvements. And for RTOS hardware replication, systems like Silicon Trons have explored replicating the entire RTOS in hardware, reducing latency and improve predictability. While these techniques enhance system performance, but we have more studies failed to integrate power-saving methods with offloading approaches. And why this paper uses the RTOS offloading techniques, because we have some advantages like reduced context switch delay. Offloading techniques can reduce context switch delay by transferring this operation to dedicated hardware or core processors, and improve scheduling predictability. Like offloading improves RTOS scheduling predictability by eliminating jitter effect associated with software-based context switching. The third is enhanced system performance. By offloading tasks, system performance can be improved as the main processor is freed up to focus on applied tasks. Reduce power consumption. In certain scenarios, offloading can lower power consumption by reducing the workload on the main processor. And the next is comparison of related work with the proposed work. The proposed solution integrates unique features that are absent in some prior works, combines voltage scaling, frequency scaling, and clock gating in a real-time system. Uses free RTOS for a more robust, lightweight RTOS with offloading capabilities, and support high-end soft real-time capabilities with advanced task scheduling techniques. And this table is for the comparison of related work with the proposed work. Like there are many platforms like ARM, Cortex, EVA, and ODSU3, and the proposed solution using is the XC7G020, and real-time capability. Like this is the combination of a hard and software. And a key insights platform showing the hardware use. Example like ARM and or FPGA models like XC7G020. Real-time capability. Differences between soft and hard real-time requirements. Scheduling algorithm indicates the type of stack scheduling used, such as EDF, LST, or FPP. Operating system highlights the operating system employed, like Ubuntu Linux, FreeRTOS, or custom in-house solutions. And this is the power-saving techniques, voltage scaling, whether the work use techniques to dynamically adjust voltage, and frequency scaling, like here. If the processor's frequency is adjusted to reduce power consumption. Clock gating, whether idle processors use clock gating to save power. Power saving on processor and FPGA indicates if power saving methods were applied on the processor or FPGA. And the proposed solution got all of this done, so we chose this paper for our topic. The next is heuristic task mapping strategy talked about in this paper. This mapping strategy aims to optimize task allocation in a multi-core system by assigning related tasks to the same slab processing element, like 1PE, to minimize communication delays across the network on chip and OC, and balancing real-time performance and power consumption by dynamically monitoring task dependencies, inter-core communications, and PE workload. Like in this image, this is the master PE, and he distributed many slab PE and just mapping any task to the slab process element to minimize communications to the related task. And this is the architecture, like in the slab PE, this is the free RTOS and clock gating and hardware-based task scheduling like we talked about before. And this is the router. Yes, for the next page. We got some system architecture integration. The master slab configuration. The system architecture includes a network on chip and 4 PEs arranged in a master slab configuration. The master PE monitors system power consumption and dynamically adjusts voltage and manages task allocation. Each slab PE features a microblade processor for task execution. Include an NCM module for dynamic frequency scaling. Use clock gating to place the processor in a low power state during the idle period. Implement hardware offload task scheduling and frequency scaling. Slab PE dynamically adjusts their operating frequency using the NCM module based on the task requirement. Achieve a balance between performance and energy efficiency. And a key feature of this. First, we're gonna talk about is task dependency analysis. Tasks and their dependencies are represented using a DAG. It's a directed acyclic graph where nodes represent task, weight by execution time. Edge represent communication cost between tasks, and priorities are assigned based on the cumulative weight of the dependent task, ensuring that critical tasks are prioritized. The second one is dynamic task assignment. Initial tasks lost without parent dependencies are assigned to the least loaded PE, maximizing parallelism. Dependent tasks are mapped to the optimal PE by calculating a cost function. If the PE already executed a predecessor task, communication delay is reduced. Otherwise, costs are added for inter-core communication. Real-time and power balancing. Execution time for each PE is monitored to ensure balanced workload distribution. Task mapping is performed efficiently to meet real-time constraints while minimizing power consumption. And we talk about these features impact on the real-time capability. The first one, it enhances the scheduling performance. Hardware offload task scheduling improves scheduling efficiency, reducing context switch overhead by 33%. Eliminates jitter effect associated with software-based scheduling. Dynamic power adjustment. The master PE dynamically adjusts frequency of the slab PE, ensuring they meet real-time requirements while optimizing power consumption. And the advantage of this, first one is reduced communication delays. Assigning related tasks to the same PE avoids unnecessary NOC communications. Number 2 is improved efficiency. Compared to random mapping algorithm, this strategy ensures faster and more efficiency task assignment without violating real-time deadlines. The third is dynamically adaptability. The strategy continuously monitors PE workloads and dynamically adjusts task allocation to optimize resource usage. And next, we are talking about the power saving techniques of this paper. How do they save their power on an RTOS real-time operating system? And the proposed solution employs multiple power saving techniques to optimize every energy consumption in the multi-core architecture without compromising real-time performance. And this method include, I think, is a 3 method, 4 method, like dynamic voltage and frequency scaling (DBFS), and clock gating and voltage adjustment. First one we are talking about is dynamic voltage and frequency scaling. The method. Dynamic adjusts the processor's frequency and voltage based on their task requirements, and higher frequencies are used for performance critical tasks, while lower frequencies are applied for less demanding tasks. And the result, as the task period increased, the power consumption decreased significantly. Power reduced from 3700 to 100 NW. Compared to an unoptimized design. Minimum power saving of 9% at the lowest cycle, and maximum power saving of 67% at highest cycle. Impact: DBFS ensure the power is optimized for each task while maintaining real-time constraints. A next method is clock gating. Clock gating shuts off all the clock signal to idle cross or unused parts of the processor to minimize power usage during idle states. Clock gating alone achieves 46% on power saving, while it's the lowest test cycle, and 68% power savings at the highest task cycle. When combined with DBFS, and save a lot more energy, like at a low cycle and high cycle. And impact: clock gating is high effective techniques for minimizing idle power consumption, especially when integrated with DBFS. And the third is voltage adjustment method. Dynamically reduce the supply voltage of the process elements to a lower level, while still maintaining operational stability. And the results: it reduced the energy consumption by 70%, even 90%. Impact: the voltage adjustment provides substantial energy efficiency improvements, and especially for longer task duration. It's the conclusion and future work. Like this paper talk about three things: is the power saving techniques and their task mapping strategy, and the comparison of the related work, like advantage of RTOS offloading techniques. This paper mainly talk about three big points from this RTOS and mapping strategy and power saving techniques. So this is the three main point of this paper, and they combine these three point to minimize the everything on the RTOS system. This is the conclusion and future work. Like evaluation, hardware platform. The proposed system was implemented on a FPGA-based multi-core architecture using a NOC and 4 process element PE in a master slave configuration. Each slave PE integrates microblade processors, NCM module for frequency scaling, and clock gating mechanics. Software environment. Free RTOS was used as an operating system to support real-time scheduling and task offloading. And the next one is metric evaluate. Real-time performance, like context switch overhead and jitter reduction. Power and energy consumption, impacts of DBFS and clock gating or voltage adjustment. Task mapping efficiency, like executing time and resource utilization. The summary of the contribution. This study proposed an energy-efficient multi-core architecture integrating RTOS offload methodologies, power-saving techniques, and heritage task mapping strategies. Key contributors include, as we talked about before, which they improve the hardware offload tasks by 33% while eliminating jitter effects, and integration of dynamic voltage and frequency scaling, DBFS, clock gating, and voltage adjustment, and just overall they reduce the power by 47% and energy consumption by 90%. Real-time and energy efficiency. The architecture successfully balanced real-time performance with energy efficiency by dynamically managing task allocation and power consumption in a master-slave multi-core system. The heuristic mapping strategy minimizes inter-core communications, delay, and enhance resources utilization while meeting real-time constraints. That means they want to fit the real-time operating systems, but not to reduce his any power or energy consumption. So this is the purpose of this paper. Yeah, and this is the conclusion about this paper, and we will talk about future work. The future work of this paper. The first one is scalability, and they want to extend the architecture to support larger multi-core systems with more complex task dependencies, and explore the performance of the heuristic mapping strategy in heterogeneous multi-core environments. 2. Advanced power-saving techniques. Investigate more sophisticated power-saving methods, such as machine learning-based dynamic voltage scaling or adaptive clock gating strategies. Enhance the granularity of voltage and frequency adjustments for finer power control. The third is real-time system integration. Test the proposed solution with other real-time operating systems like BetaWorks or QNX to evaluate its adaptability and performance. Integrate with real-world workloads in domains such as automotive systems, robotics, and IoT. And the fourth is the network-on-chip optimization. Optimize the NOC architecture for further reducing inter-core communication delays and power consumption. The fifth is the experimental validation. Perform extensive validation on physical hardware platforms, incorporating diverse task scenarios to further verify the proposed system's reliability and efficiency. And that's the end of this paper. We summarize the 3 big points of this paper. There are many stats and image on this paper, but the main point of this paper is these 3 big things. So we just talk about the 3 things. If anyone interested in this paper, how it works, you can click the link in my very first page. You can click here and learn more about this paper. Thank you for your listening.